It's the end of April here in Mumbai in 2025 as I'm recording this, and it's hot, folks. It's not called a heat wave because it's not, it's normal, but nonetheless, I've been recording a few papers uh, as podcasts summarizing a few papers on heat wave impacts and so on. So this is called Mortality Impacts. Oops. I hate this. Mortality impacts of the most extreme heat events. It's a review paper. We'll just read the abstract, few papers, and some summary and recommendations. Extreme heat threatens human life, evidenced by more than 260,000 heat-related fatalities collectively in the deadliest events since 2000. So they are not taking all heat waves, they are taking the most extreme heat events. In this review, we link physical climate science with heat mortality risk, including crossings of uncompensable thresholds beyond which human core body temperatures rise uncontrollably, and unsurvivable thresholds, which is lethal core temperature increase within 6 hours. Uncompensable thresholds where wet bulb temperatures are in the range of 19 to 32 degrees C, depending on where you are, depend strongly on age and a combination of air temperature and relative humidity, which you are probably already aware. I have other podcasts on that if you want to follow up. These thresholds have been breached rarely for younger adults, so about 2.2% of the land area over 1994 to 2023, but more widely for older adults at 21%. Survivable thresholds with wet bulb temperatures of 20 degree to 34 degrees C were only exceeded for older adults, 1.8% of the land area that accounts for those effects. More anthropogenic warming will lead to more frequent threshold crossings, including tripling of the uncompensable land area for young adults if warming reaches 2 degrees C above the pre-industrial levels. Interdisciplinary work must improve the understanding of the deadly potential of unprecedented heat and how it can be reduced. Ensuring reliable access for all to cool refugia is an urgent priority as the atmosphere threatens to increasingly overwhelm human physiology under climate warming. So you can see that they are doing it slightly differently. They're trying to look at how much area will be covered by these uncompensable and unsurvivable thresholds in terms of the measures that indicate human physiological limits. So let's define here the heat and heat related terms, just for some of this is repetition, but it's okay. Formally, heat is a type of energy transferred between systems. Informally, however, it describes a property that the atmosphere possesses. The appropriate term for this possession is, instead of enthalpy H, which depends on the internal energy of the air U and the pressure P, volume V product, so H enthalpy is U plus PV. U is proportional to dry bulb temperature TA of the air, with specific heat at constant volume being a constant of proportionality, so U is CV times TA, the internal energy. Sorry, somebody is remembering me, I'm having hiccups. Under isobaric conditions, heat transferred to a parcel of air raises U and performs work by increasing V, so volume increases. The increase in H can be evaluated from TA using the specific heat of air at constant pressure in that case, so delta H then becomes Cp times delta TA. Substituting the actual temperature in Kelvin into equation 3 here yields the change in enthalpy relative to absolute zero, which is often referred to as the sensible heat content. Basically, if there's a temperature difference, then that heat gets lost through sensible heat loss. The energy associated with water phase changes can be added to the sensible heat content to define moist enthalpy E or ME for an air vapor mix. E is CPTA plus LVQ, latent heat of vaporization, and specific humidity. Do you really need these? Well, if you're a doctor, probably not, but if you're an engineer or a climate scientist, you want to probably pay attention to these. Maybe some doctors, epidemiologists have to pay attention as well. Uh, this collectively describes the latent heat content. E divided by Cp is the equivalent temperature monotonically but non-linearly related to the wet bulb temperature Tw, the temperature of an air parcel cooled to saturation at constant pressure by evaporation of water into it with the increase in latent heat content supplied by the sensible. Well, some details there that let's not bother with. Okay, so what are the human heat balance and thermal physiology then? Heat balance of a naked body is influenced by various processes that we will look at here. Heat is exchanged between the skin and the atmosphere via sensible heat exchange, so convection scaling with gradients of dry bulb temperature. So if humidity is not involved, then the body heat and the air temperature, body temperature and air temperature, skin temperature that is, will drive sensible heat loss. So if you blow a fan, you will feel cooler, but if it's humid, you know it's an entirely different story. But human mortality is attributable to extreme heat. Human mortality attributable to extreme heat is not typically from hyperthermia. In general, the myriad of pathways to heat-related deaths, such as cardiovascular, renal, and endotoxemia result from blood temperature being a high priority homeostatic variable defended at the cost of other systems such as fluid balance, blood flow delivery to central organs. So body tries to deal with blood temperature in a prioritized manner while ignoring other things. These same pathways, even when they do not lead directly to death, are associated with heightened morbidity, which is the sickness you get from exposure. But basically we are talking about attribution of heat wave itself to mortality can be tricky. There are many details there that I'm not going to get into, but essentially there are maybe pre-existing conditions like cardiovascular, renal, and endotoxemia that can result in death. But then the question really becomes, if let's say an insurance company is trying to decide whether you died of heat wave or something else, right? So in general, people say it's easy to estimate mortality due to heat wave because you can just look at excess deaths in a given period. If you have an average number of deaths that occur at a particular place, then when a heat wave occurs, you can look at the number of deaths and say how many are excess compared to what is generally expected. But insurance companies may not be able to accept that as proof of heat wave impacts, right? So solar radiation, of course, is a heat source, and it's harder to avoid if there is direct heating. So we also have global wet bulb temperature that we look at, which takes into account whether you are in the shade or other effects are taken care, or you are directly in the sun and so on. Long wave radiation is the thermal output from the body. So it's like a black body radiation. I'm not going to go too much into the details, but basically the per unit area is going to depend on the geometry and emissivity and other details. Sweat evaporation, latent heat can be lost by evaporation, of course, and then you have to worry about wet bulb temperature, because the loss is going to depend on how saturated the air is. If the air is already saturated with water vapor, which is what wet bulb temperature is, then the body is unable to evaporate that sweat and cool the body, right? Metabolism always represents a source of internal heat gain. Metabolic heat generation increases with rising intensity of physical activity. For most activities, heat production is nearly equivalent to energy expenditure, but the former accounts for less of the latter as external work increases, for example, from lifting the body against gravity when walking uphill. Convection then is the sensible heat loss from the body by convection when skin temperature exceeds the air temperature. So body loses heat directly by air currents taking the heat away. The rate of exchange increases with the Ts minus Ta gradient and with air velocity, which is why a fan can help very well in dry temperatures or you can take off the shirt and whatever and feel cooler because you know, increase the exposure to air or ambient temperature, which is cooler than the body temperature. Just jumping ahead, it's a review paper, so it's a long paper and there's a lot of good discussion on various details that I'm skipping here. This is observed and projected extreme heat. So this is maximum observed dry heat. You can see, of course, Sahara, Middle East, Northwest India into Afghanistan, Iran, and then parts of Australia, and so on, and as well as here, South East, Central US, etc. But if you look at maximum observed humid heat, so this is in sensible heat kilojoules per kilogram, and this is moist enthalpy joules per kilogram. So you can see now slightly different regions light up. So this is a desert, so the humid heat is not as extreme as the dry heat, but there are regions which light up, and lots of the US here lights up, but you have to be careful because the scales are different here as well. Okay, observed warming rate of the air temperatures. There are certain hot spots, Mediterranean and the Middle East, and in all this warming, India is surprisingly not warming, and there are you know, there's a recent science article by Vaishnavi Chandrasekhar that talks about this. Basically, we don't know exactly why that's happening. Observed wet bulb temperature warming rates. So now you have something else happening which explains the rapid warming here. For example, with warming, if you increase humidity, then water vapor is a strong greenhouse gas, and you can have rapid warming as well. These are projected, depends on the scenario used. They use here ERA 5 CMIP 6 data. What is the scenario used for projections? So E and F. Projected warming rate for from 1960 to 2100 using an ensemble of 16 CMIP 6 models. That's the last IPCC assessment report. I won't go into the details because there are many scenarios which will give you different answers, and there are, if you go out to 2100, there are uncertainties just resulting from the scenarios that are assumed to make these projections. So you have to you know, go and read it yourself if you are interested. There are a lot of people writing papers on what will happen by 2100 to heat waves and droughts and extreme rainfall and so on, but I am not a big fan of the projections beyond a couple of decades. In the first couple of decades, it's all model uncertainty, internal variability, and then it's all scenario uncertainties, and scenarios are just made up. If you look at what's happening in the world with all the wars, then you know that the scenarios are whatever. Okay, so frequency of extreme heat in terms of percentages with warming levels, which is a better way to look at it, but these are global numbers which are not going to be very helpful locally. Ultimately, you want to understand what will happen locally. So here you are looking at the sensible heat and the air temperatures reaching 43.35 degrees C and TW max. So you have frequency of unprecedented heat and frequency of extreme heat, of course dry versus wet, and so on and so forth. That I'm not going to worry about, but you can see the uncertainties are quite large as well. The upper limits of human tolerance is something that gets discussed a lot conceptually. Statistical modeling of future heat mortality is challenged by the need to extrapolate to warmer climates in which physiological considerations identify the potential for a sharp upward inflection in mortality if key thresholds are breached. First, moist enthalpy cannot be dissipated to an atmosphere with higher total heat content, which means that core human body temperatures must, subject to no other means of heat exchange, rise if this limit is breached. So body cannot lose heat, then core temperatures begin to increase. Second, death is inevitable is the inevitable consequence of unchecked core temperature increase owing to fundamental biophysical limits. It can lead be related to protein denaturation, which was in box 2, but I didn't read because I didn't want to go into those kind of details. Identifying the limits in thermoregulation for humans and the extent to which they are crossed at different warming levels is therefore critical. Once breached, direct heat deaths could rise sharply, an inflection that might be missed by the statistical projections if calibrated mainly on the indirect, so mostly cardiovascular and respiratory causes of heat mortality dominating the past. Heat thresholds beyond which core human body temperature cannot be prevented from rising uncontrollably, see uncompensable threshold, and the thresholds beyond which this core temperature rise can reach at almost certainly lethal 42 degrees C within a specified period. That's the unsurvivable threshold, and they are now being explored. You can look up their supplementary text. In all cases, thresholds are defined for scenarios without solar radiation, an additional heat source critical for assessments of livability, but less relevant for survival situations in which it is assumed that sunlight would be avoided, so you are not out there in the desert by yourself. Note that the terms uncompensable and unsurvivable are used to describe conditions exceeding physiological thresholds. So there's lots of assumptions involved. This is kind of a long caption, but you are looking at various quantities. Here you are looking at air temperature, and here you are looking at relative humidity proportion. So this is the density, 1 hour maximum humidity distribution, 6 hour maximum humidity distribution. So those are thin and thick red lines. Chamber uncompensable threshold, younger adults, so you are doing experiments. Chamber uncompensable threshold for older adults drops to a lower, so obviously younger people can tolerate higher temperature and relative humidity than older ones. Uncompensable threshold, younger adults, unsurvivable threshold, and so on for older adults. So the thin lines here are the wet bulb temperature thresholds. Okay, so this is Paris, Karachi, Vancouver, Lagos. The ranges are different. In Paris, you have air temperatures going up to 55 degrees. Well, actually, there is this is what you have to look at versus the reference temperatures. Okay, so you can see that these are all the same in all figures. These purple, blue, light purple, and light blue lines. So these red lines are what you are looking at in terms of actual observation. So those are heat and humidity during the deadliest heat wave events. Density of dry heat, TA relative to humidity, RH combinations during, so TA RH combinations during the all-time highest hourly heat index values for each grid point over 1994 to 2023 in ERA 5, the reanalysis product. The black rectangle here highlights the most frequently occurring TA-TH relationship combinations, and you can see those here as well. Obviously, Paris is not going to get as hot as Karachi, and Lagos is very hot as well, similar to Karachi, but Vancouver is much cooler. But it's the relative exceedances of that background mean temperature that's going to matter in terms of mortality. You remember the big heat waves in Europe killed some 70,000 people and so on. Okay, more details so B is as in panel A, but for all hours during deadly heat events in Paris, France in 2003, which killed over 75,000 people in Europe, I think, using ERA 5 data and so on. But you get the idea that basically we are talking about mortality coming from most extreme heat events. What is this good for? Doesn't change the basic actions needed in terms of early warnings and shelters, hydration centers, hospital access, and so on. The trick is always the adaptation measures for workers outside. We looked at industrial workers indoors, but farm workers and construction workers and so on. There are ideas on changing work hours and avoiding peak heat hours and so on and so forth. Okay, so these are observed crossing of uncompensable and unsurvivable thresholds that have already occurred. Observed means already occurred. So this is for 1994 to 2023. So this is good because you have to separate uncompensable and unsurvivable for younger adults and older adults. So these are probability of exceedances. This is 1 hour, and you can see India's hot heat wave belt is there here. If you do 6 hours, it drops, but obviously if it lasts for 6 hours, mortality will be higher, even though here depends on whether you are older or younger. So you can see the difference here. For younger, it's very different. These two just focus here. But for older ones, this is still similar in terms of the probability of exceedance. Okay, so this is unsurvivable at 6 hours for younger and older, and there's been no observed unsurvivable thresholds, but for older adults there have been in MENA, Middle East and North Africa, as well as into Pakistan, Afghanistan. Pakistan is very hot. It's heat wave season. For India it's March, April, May, and then rainfall arrives in June typically, but for Pakistan it's into July, and they have been having 50-degree heat waves pretty much every year recently. So some things to keep in mind. Okay, so this is warming to exceed uncompensable threshold in younger adults, and this is warming to exceed unsurvivable thresholds in younger adults. So projections, there is no good news. This is for older adults, many more regions getting to thresholds of uncompensable and unsurvivable thresholds. Okay, so that's again putting Paris, Karachi, Vancouver and Lagos in context for 2003, 2015, 2021 and 2024. Okay, so I'm being brief because message is loud and clear. So let's read some summary and future perspectives to just get a sense of what the paper is talking about. I'm again being brief here, so I've cut out lot of the future perspectives as well, but you should read the paper if you're interested in more details. Understanding of the most extreme heat events and their exacerbation with climate change is improved. Large ensemble climate modeling has characterized heat events beyond historical norms, whereas moist convective framework has identified their theoretical upper limits. Large ensemble, if you don't know what that is, you can ignore it, but basically you want to understand the internal variability, which is better done if you have lots of simulations of a climate model. Then you know what is exceedance because of anthropogenic impacts versus what is possible in 1 in 50-year event, 1 in 100-year event, 1 in 200-year event, and so on and so forth. Okay, observations and model projections agree that extreme dry heat over land areas increases faster than global mean air temperature, exceeding twice the rate in key hotspot regions such as Amazonia and Western and Central Europe. Physical upper bounds on extreme air temperature in mid-latitude regions, which can be around 10 degrees C higher than the observed maxima, even without further climate change, what we already have. And these are increasing at a similar rate, leaving high potential for record-shattering air temperatures. In the regions suffering the deadliest recorded heat events, this is what is happening. Observations, so let me read that again, I kind of emphasize it in a funny way. Physical upper bounds on extreme air temperatures in mid-latitude regions, which can be ordered 10 degrees C higher than observed maxima even without further climate change, are increasing at a similar rate, leaving high potential for record-shattering air temperatures in the regions suffering the deadliest recorded heat events. Observations, model projections, and convective theory generally agree on more spatially uniform changes in wet bulb extremes, generally increasing by less than 1 degree C for each degree of warming for tropical and subtropical regions where wet bulb temperature has historically been highest. There is some arguments on how the troposphere adjusts and how wet bulb temperatures adjust, and I have a separate podcast on that you can follow up. Basically, people kept talking about exceeding these survivability limits in terms of wet bulb temperatures, and people looked at the dynamics of how the troposphere adjusts in the deep tropics and showed that even with 2 degrees C warming, we are unlikely to exceed that threshold. But that's just a scientifically robust way to say it. But in terms of risks, you don't want to wait till you reach the limits anyways. On the side of human impacts, more work is needed to understand contemporary and projected risks. As a priority, better representation of the hottest and least developed regions in heat mortality databases is required, with Africa and South Asia especially in need. However, understanding the impacts must go beyond epidemiology and physiology, drawing on the social sciences to grapple with the relevant complex socioeconomic, political, and cultural factors that modulate heat mortality. So, in a city like Mumbai, the same heat wave can have very different mortality and morbidity impacts based on whether you are living in poor slums or in high-rise rich places, or you are working outside or in your office, and so on and so forth, right? Specifically, chronic and short-term drivers of exposure to extreme heat and the barriers preventing individuals adopting life-saving cooling behaviors during extreme events should be priorities for research. Detailed case studies using qualitative methods could help develop deeper understanding in this regard. These efforts should also draw on emerging understanding of the way that compound weather hazards can increase vulnerability to extreme heat, integrating counterfactual thinking exercises to identify particularly dangerous but as yet unseen combinations. Counterfactual thinking is basically where you imagine what would happen if global warming didn't happen, heat waves didn't increase, and so on. Interacting indirect pathways to extreme heat mortality must be included in such assessments, for instance, related to infrastructure failure, food security, economic shocks, and conflicts, not least because the wider biosphere is universally characterized by upper physiological limits to heat tolerance that are increasingly at risk of being exceeded. Okay, so that's kind of the context for this heat waves and most extreme heat waves and mortality. As I said, this is a nice long review paper, but if you want more details, you need to follow up. I was trying to be brief, so obviously I skipped many details, but those details are in fact very interesting, and since it's a review paper, obviously it has lots and lots of references that are very useful as well. Okay, see you in another topic on heat waves.